Lenz law. So Lenz law states that an induced electric current always flows in such a direction that it opposes the change producing it. This law is essentially a form of the law of conservation of energy. An illustration of Lenz's law can be explained by the following experiment. For the first experiment, in figure 5.6, the magnitude of the magnetic field at the solenoid increases as the bar magnet is moved towards the solenoid. An EMF is induced in the solenoid and the galvanometer indicates that a current is flowing. To determine the direction of the current through the galvanometer, which corresponds to a deflection in a particular sense, the current through the solenoid sense is in the direction that make the solenoid at the upper end become a north pole. This is to oppose the increases of the magnetic field from the bar magnet. So by using the right hand grip rule, when your thumb pointed upward based on the direction of the north pole, so we can indicate the direction of current by your hand grips. Second experiment. So we consider a straight conductor PQ is placed perpendicular to the magnetic field and move the conductor to the left with constant velocity. For this figure 5.7, so the magnetic field is pointed into the page and the bar and the conductor is moved to the left. When the conductor is moved to the left, the magnetic flux is increased since the swept area is increased. When the conductor moves to the left, the induced current need to flow in such a way that it opposes the change which has induced it. So, to oppose the magnetic flux, the magnetic field is seen to be into the page. Because to oppose the increasing of magnetic flux. To determine the direction of induced current through the conductor, we can use the Fleming left-hand rule, which is the direction of thumb represent as the direction of the motion, and your first finger is direction of field, and the second finger is refer to the direction of induced current. So for this example, since the direction of induced magnetic field is into the page and the V is to the left, so by using the Fleming left-hand rule, the direction of currents is actually seen to flow from Q to P. So that's why the galvanometer seems deflect in such a direction. Third experiment. Consider two solenoids P and Q arranged coaxially close to each other as shown in figure 5.9a. At the moment when switch S is closed, current I begin to flow in the solenoid P. And producing a magnetic field inside the solenoid. By using right hand grip rule, so we can determine the direction of magnetic field. At this end of solenoid is north pole and this is a south pole. So suppose that the field point toward the solenoid Q. When the magnetic flux through the coil P increase, therefore the magnetic flux through solenoid Q also increase with time. According to the Faraday's law, an induced current due to the induced EMF will exist in solenoid Q. The induced current flow in solenoid Q must produce a magnetic field that opposes the change producing it, which is increase in flux. So that's why the end of the solenoid Q, which is in front of the P, will act as a north pole because to reduce the magnetic field from the solenoid P. Therefore, by using right hand grip rule, okay, the induced current in the circuit is anti-clockwise. Example 5.7. We have a singleton of circular shaped coil which has a resistance of 20 ohm and an area of 7 cm square. It moves toward the north pole of a bar magnet as shown in figure. If the average rate of change of magnetic flux density through the coil is 0.55 Tesla per second, A. Determine the induced current in the coil, and B. State the direction of the induced current observed by the observer shown in figure 5.10. First of all, okay, the information given is the resistance of the coil 20 ohm and the area of coil is 7 cm square. And we should know that 0.55 Tesla per second actually refer to the rate of change of magnetic field. So, according to the Faraday's law, which is the induced EMF is directly proportional to the rate of change of magnetic flux, thus we have the equation is induced EMF negative, okay, and by refer to the number of turn for the coil and rate of change of magnetic flux. So, flux or phi in this equation is actually BA cos theta. And the theta for this case, since we have the circular coil, okay, and this is the direction of magnetic field, okay, this is the direction of vector A. That's why the theta in this case is actually 180 degree. So we rearrange the equation. Okay, we got the phi 5 equal to negative BA. Okay, when we rearrange the equation, the constant value, okay, we write down the constant value which is number of turn times with the area. Okay, and we got the equation for rate of change of magnetic field, which is already given in the question 0.55 Tesla per second. Okay, and then we substitute the quantity given, number of turn which is singleton, so n equal to 1. Okay, and the area given 7 power of negative 4 meter square, and the rate of change of magnetic field is 0.55. So the induced EMF in this circular coil is actually 3.85 power of negative 4 volt. Therefore, the induced current in the coil is actually from the formula of EMF equal to IR, and the induced EMF which is calculated 3.85 power of negative 4. Okay, and the I induced and the resistance of the coil is 20 ohm. Therefore, the current induced is actually 1.93 power of negative 5 ampere.
A straight conductor that is moving at the speed v in a uniform magnetic field B. After some time, it has moved to this new position. So what do we mean by flux cut? You can imagine the conductor as a blade of a knife that is moving through this field and the field lines as grass. As the blade moves through, it will be cutting through the grass. Since there is flux cut, Faraday's law predicts that there is an EMF induced across this conductor, and the EMF induced, its magnitude, will be equal to the rate of flux cut. Now, to find the rate of flux cut, we will first need two quantities, the magnetic flux density B and the area that the conductor has cut. Let's assume that it has moved through a distance of delta x in a time of delta t. The area of the field cut by the straight conductor is this red area here and is therefore equals to L times delta x. Hence, the magnetic flux cut by the conductor is given by B times the area that it's cut, and it is BL delta x. The rate at which flux is cut is therefore written as the total flux cut divided by the total time taken, which is BL delta x divided by delta t. Now, we know that delta x over delta t gives us the speed v. Hence, we can write this as VLV. Therefore, the EMF induced